For decades, the Big Bang has been the generally accepted model for the origin of our universe. But now, scientists say we've been wrong about the Big Bang and the universe. New observations and data suggest that the universe may not have originated quite as we learned in textbooks. One of the biggest problems is the so-called lithium problem. Together with a matter-antimatter imbalance, it is shaking the foundations of our cosmology and possibly opening the way to a completely new worldview. The Big Bang was a tremendous expansion impulse from an extremely dense point. At least, that was a prevailing view for a long time. However, the latest discoveries by the James Webb Space Telescope and a growing number of voices in the scientific community are calling this theory into question. The lithium problem is currently the focus of scientific attention. Calculations based on the Big Bang theory predict a precise amount of light lithium that should have been created in the first few minutes after the Big Bang. However, when astronomers now search the JWST data for traces of these lithium deposits in extremely old stars, they find only a fraction of the expected amount. This contradiction was already known before the launch of the new space telescope, but now the situation is becoming increasingly clear. Hubble and other ground-based telescopes have already discovered very old stars in the universe that should have shown traces of lithium concentrations, but no such luck. The figures did not match, not even approximately. The JWST's discoveries go even further back in time, and there, too, no high lithium concentrations have been found. How does this fit together, and is there still hope for the Big Bang theory? An alternative explanation could be the galactic origin of light elements model, or GOLEM for short. Here, lithium does not originate in an initial cosmic fireball, but through slow processes in the first generations of stars. According to previous ideas, these early stars enrich the universe not only with light but also with the building blocks of life over many millions of years. Another problem that we urgently need to shed light on is the so-called surface brightness of distant galaxies, or the distribution of matter and antimatter in the universe. You are matter-antimatter dissonance. One of the most fascinating and mysterious questions in modern physics is the so-called matter-antimatter problem. It concerns nothing less than the existence of the universe itself and the exciting question of why matter and life formed in the universe at all, instead of everything dissolving into a sea of energy. To understand this, we need to take a closer look at the concept of matter and antimatter. Matter consists of building blocks such as atoms, electrons, protons, and neutrons. Everything that has mass and takes up space, stars, planets, living beings, is made up of matter. In theory, there can be a corresponding antiparticle for every particle within matter. The electron has a positively charged counterpart called a positron. The proton has a negatively charged antiproton, and so on. These antiparticles have exactly the same mass but opposite electric charges. When a particle encounters its antiparticle, they cancel each other out, in a sense. Scientists say they annihilate each other, disappear, and release energy, which typically manifests itself in the form of high-energy radiation. According to the standard model of physics, matter and antimatter should have been created in exactly equal amounts during the Big Bang. Physically, it would make no sense for one to have been favored over the other, but reality shows us something different. The observable universe consists almost entirely of matter. Antimatter occurs practically only in artificial laboratory conditions, or as particles in cosmic radiation. No galaxy, no star, and no living being consists of antimatter. Here comes a great paradox. If equal amounts of matter and antimatter had formed after the Big Bang, they would have destroyed each other. The universe as we know it would never have come into existence. All that would have remained would be radiation, no light, no atoms, no structures, no life. So there must have been a tiny asymmetry, an imbalance in which slightly more matter than antimatter was created. A surplus of perhaps 1 particle per billion would have been enough to create everything we can see in the universe, including ourselves. Without this minimal surplus, the universe would have immediately dissolved into nothingness after Big Bang. But why was there this deviation? Was it intentional, a divine blueprint, or pure coincidence? Physics refers rather matter-of-factly to a CP violation, a violation of what is known as charge parity symmetry. This means that some particles and their antiparticles do not behave in exactly the same way, although such effects have been observed in experiments. For example, in the decay of certain mesons, they are still not sufficient to explain the current dominance of matter. This means that there must be further explanations, such as previously unknown processes or particles that tip the cosmic balance slightly in favor of matter. The latest discoveries and all the problems in current physics point to these as yet unknown and unexplored aspects. Concepts such as baryogenesis and leptogenesis attempt to trace the matter-antimatter asymmetry back to processes that took place shortly after the Big Bang. Other hypotheses attempt to explain the existence of matter via parallel universes in which antimatter dominates. This would be a kind of cosmic balance in the multiverse. However, all these ideas remain pure speculation without any real evidence. The problem of matter-antimatter asymmetry is therefore more than just an open question in particle physics. It is a fundamental gap in our understanding of the origin of the universe, baryogenesis and leptogenesis, flaws in the standard model of particle physics. It's like a cosmic mystery. As we follow the clues of the magical imbalance in the universe, we arrive at baryogenesis and leptogenesis. If matter and antimatter were created in equal amounts during the Big Bang, why is almost only matter left today? When baryogenesis and leptogenesis attempt to explain the tiny imbalance between matter and antimatter, we dive deep into the world of particle physics. Baryogenesis refers to the creation of an excess of baryons in the early universe. Baryons are particles such as protons and neutrons. According to theory, shortly after the Big Bang, there must have been a phase in which physical processes violated symmetry, resulting in a slight excess of matter. Returning to the so-called CP violation, matter and antimatter behaved slightly differently in certain situations. This tiny asymmetry could have been enough for a small portion of matter to remain in the end while the rest destroyed each other. Closely related to this is leptogenesis. Leptons are particles such as electrons and neutrinos. In some theories, such as the seesaw mechanism, extremely heavy right-hand neutrinos play a central role. These hypothetical particles could have decayed in the early universe, creating an asymmetry in the leptons. Later, this lepton asymmetry was converted into a baryon asymmetry. Among other things, so-called Sphaleron processes, which play a fundamental role in the standard model of particle physics, were involved in this. Although both models are mathematically consistent and could answer many questions, experimental evidence is still lacking. Neither the necessary heavy neutrinos nor clear new sources of CP violation have been discovered. New research at CERN and with the Large Hadron Collider in Geneva is expected to greatly advance neutrino research in the coming decade and solve these problems in particle physics. Perhaps we will then know how the perfect balance of the Big Bang gave rise to the small imbalance that made everything possible, including us, antimatter universes, dark mirrors, and the great cosmic balance. What if our universe is not the only one? And what if, in another hidden cosmos, antimatter rather than matter is a dominant principle? This question sounds like science fiction, but it's a reality of modern theoretical physics. If exactly the same amount of matter and antimatter was created during the Big Bang, the question inevitably arises, where did the missing half go? Oh, to put it another way, did antimatter disappear altogether, or did it simply manifest itself elsewhere? One fascinating hypothesis is that of the mirror universe. In this anti-universe, we have structures similar to those in our cosmos, only they are made of antimatter. In such a scenario, the universe would have fallen apart into two parts after Big Bang, matter in our universe and antimatter in another. The overall balance would remain the same, only the distribution would be separate, and we would then have to live with the fact that there is an anti-imprint of our world. This idea is a symmetrical solution to the matter-antimatter problem, and might also explain why certain properties of the cosmos, such as the alignment of physical constants or certain gravitational anomalies, are so difficult to explain. But if this anti-universe exists, then it must somehow be related to ours, and we should be able to locate it as our science progresses. The speculative assumption goes even further, suggesting that dark matter, which is thought to make up around 85% of the mass in the universe, is actually antimatter. Perhaps this is not missing mass in the classical sense, but a kind of shifted reality, an antimatter world that interacts with ours only through gravity but does not respond to any other forces. This would also explain why we have not yet been able to detect dark matter directly, even though its gravitational effect on galaxies and other large objects in the universe can be observed everywhere. Such ideas are naturally closely linked to multiverse theories, which originate from quantum physics and have become increasingly prominent since a confusion in classical physics. If our universe is only one of many, Each of these universes could have its own physical rules, explaining and balancing out dissonances in our universe. Proportions of dark matter, antimatter, and other curiosities, such as a time paradox, could be explained if the missing parts are found in other dimensions or universes. If we take everything together, we then have the golden cosmic balance. Again, these considerations are still purely theoretical. There is no experimental evidence for an anti-universe or for antimatter dark matter. Even the assumption that there must be a strange balance could be a serious mistake. All these unanswered questions show how big the gap in our understanding of our origins and the universe still is. We know more and more, and yet still so little. Sometimes in science, it seems as if every discovery and every mystery solved complete a map on the one hand, but, on the other hand, reveals that entire countries and continents have been forgotten or not yet discovered on that map. There may be dimensions beyond this map, or researchers may have to realize that there are phenomena, other spaces or forces within the known lands, that are still far from being understood.